or he calculated the radius of the orbit, and any electron on the orbit has a speed v. The speed of the electron also can be calculated by the relation mvr equal nh over 2 pi. And Bohr calculated the energy, the total energy of the electron on certain orbit, E equal minus 2.18 times 10 minus 18 divided by n square z square in joule, or minus 13.6 divided by n square times z square in electron volt. So the Bohr calculation talk about the excitation of the electron from one orbit to another orbit, or from one energy level to another energy level, by absorbing exactly the difference of energy between the two levels. So for example, if the electron is at level 1, which is the ground state, that will pass to level 2, the atom should absorb exactly delta E equal E2 minus E1. Bohr calculated that delta E equal E final minus E initial, and this is delta E absorbed. When the electron returns from the final state to the initial state, it will emit light of frequency mu. So delta E absorbed equal E final minus E initial equal delta E emitted. So E absorbed equal E emitted equal H nu. In the previous slides, Bohr calculated the energy E equal minus 13.6 divided by n square z square in electron volt, or minus 2.18 times 10 minus 18 z square divided by n square in joule. So Bohr put the energy as the formula he calculated, and the calculation is not requested in your curriculum this year. So he found that 1 over lambda equal a constant 1 over n final square minus 1 over n initial square. So this is the value he found by this method agrees with the Rydberg constant, and the formula deals with Balmer-Rydberg formula 1 over lambda equal RH 1 over n final square minus 1 over n initial square. So what is the importance? The importance of this theory of Bohr theory, he explained the transition and the emission of the light in hydrogen atom. He applied the formula found En equal minus 13.6 divided by n square times z square in electron volt, and he found another formula of another scientist, which is the formula of Balmer-Rydberg. So the Bohr theory applied for hydrogen atom is a true model, okay, because it's supported also by the Balmer-Rydberg formula. Example 1.6, calculate the wavelengths of light emitted when the electron in hydrogen. Pay attention that till now the Bohr theory is only applied for hydrogen or for systems of one electron in the transition from n equals 6 to n equals 5. I prefer to use the term transition from lower to higher, and from higher level to lower level I prefer to use the term emission. So in this case, we have to calculate the energy of level 5. Energy of level 5 equal minus 13.6 divided by 5 square, and Z equal 1 since we talk about hydrogen, and E6 equal minus 13.6 divided by 6 square. So delta E equal E final minus E initial equal E6 minus E5. So we calculated delta E. But delta E found in this example is in electron volt, and this is not the international system. If I write delta E equal now H in U, I will use H in the international system and the mu in the international system, so delta E should be in the international system. In this problem, in this exercise, we prefer to use En in joules. So E5 equal minus 2.18 10 minus 18 divided by 5 square. E6 equal minus 2.18 times 10 minus 18 divided by 6 square. We calculate delta E in joules. Then we say delta E equal Hc over lambda. Delta E is known, H is known, C is given. So we calculated by this way lambda, and the value obtained is in the international system 7.46 times 10 minus 6 meter. In this type of exercise, we can use also directly the Balmer-Rydberg formula, 1 over lambda equal RH 1 over 1 over N initial minus 1 over N prime, and we have N and N prime, so we can calculate directly lambda. We have two methods. We use delta E equal E6 minus E5 equal Hc over lambda, or we use directly Balmer-Rydberg formula, 1 over lambda equal RH 1 over N square minus 1 over N prime square, and we should obtain the same answer. What is the importance of Bohr theory? Bohr theory has interest and inconvenience. First, the model describes the quantized energy levels of the hydrogen atom and postulates that only certain allowed orbits, we have certain allowed orbits for the electrons. What is the meaning of this postulate? Suppose the students will enter to the classroom. The students can take his place at the stage 1 or his place at the stage 2 or stage 3. We don't have places between stage 1 and stage 2. So we say that the stage is quantized. And Bohr described that the energy is quantized. It could not take any value. So we have definite orbits. Second, as the electron becomes more bound to the nucleus, its energy becomes more negative. Why? Since En equal minus 13.6 divided by N square. When for N equal 1, E equal minus 13.6 electron volt, E1, E2 equal minus 13.6 divided by 2 square. Okay, so E2 is greater than E1. Bohr assumed that the electron could jump from one orbit to another orbit if the atom absorbs exactly the difference of energy delta E. When atom absorb energy, the electron will jump from the ground state to the excited state. When the electron returns from the excited state to the ground state, it will emit light, okay, of known frequency. Pay attention that the excitation might be in one step from level 1 to level 5, for example, but the return from 5 to 1 might be multi-step. We have several probabilities of return, and each return will correspond to a value of the wavelength lambda. What are the defects of Bohr model? Till now, we have to pay attention that Bohr model is only applied for hydrogen, which is a system of one electron and one proton, or for hydrogen-like, we called hydrogenoids, which are systems of one electron and several protons. So Bohr's theory is applied only for systems of one electron. According to Bohr, the radiation results when the electron returns from one energy orbit to another energy orbit, but Bohr did not explain the mechanism of this return. Bohr did not explain how this radiation takes place. We know that we have radiation, but what is the mechanism of formation of this radiation? Bohr did not explain. Second defect, Bohr explained the existence of several lines in hydrogen spectrum. Later, we discovered that the single line Bohr talked about was composed also of several lines very close. What is the meaning lines very close? That means the wavelengths are very close. For example, suppose we have a line in the visible spectrum, one line, and we give value 450 nanometers. When we analyze this line in hydrogen spectrum, we found that this line is composed of several lines close to each other. For example, 450, 45 nanometers. We have several wavelengths, but we see only one line. The Bohr theory explained the observed spectra for systems of one electron. For example, hydrogen, we have one electron, one proton. Or for hydrogen-like, we called hydrogenoid, like helium plus. Helium plus, Z equal 2 for helium. So we have two protons. And since we have helium plus, so we have one electron. One electron, two protons. For lithium 2 plus, we have one electron, three protons. For beryllium 3 plus, we have one electron, four protons. So this is hydrogen system of one electron, and helium plus, lithium 2 plus, beryllium 3 plus are hydrogen-like. Why we say hydrogen-like? Because it contains one electron and it contains several protons. So the Bohr theory can be applied only for hydrogen or the hydrogen-like. The Bohr theory could not be applied, for example, on sodium, which has Z equal 11. It has 11 electrons. So this is a defect of Bohr theory. What are the other defects? Bohr talk about the presence of electron on orbit. And to remember, we introduce Bohr theory by asking two questions. Why the electron, which is charged negatively, is not attracted by the nucleus, which is charged positively? So why the electron did not fall down to the nucleus? This is the first question we ask before introducing Bohr theory. The second question, any electron in motion around a center and this electron is attracted by the center will lose energy. So we'll lose potential energy, and we said that the electron will lose energy with time, so the distance between electron and the nucleus will decrease, So the electron at the end will fall down to the nucleus, so the atom will collapse, the atom does not exist. Bohr gave explanation of these two inconveniences when he said that the electron is protected on the orbit. The electron is protected on the orbit. That means the electron is in motion on the orbit, but on the same orbit it does not gain or lose energy. So the electron, according to Bohr, is protected by the orbit. When we put the hydrogen, when repeat the experiment of the hydrogen spectrum, that means we put hydrogen gas inside a glass tube, and this glass tube is submitted to a voltage. We use also magnetic field. We observe that the atomic spectrum was different from that in absence of magnetic field. For example, suppose I have one line in absence of magnetic field. So magnetic field off. When the hydrogen gas is submitted to a magnetic field, so magnetic field on, we have a splitting of one line to three lines. So that means the electron is not protected on the orbit, since the magnetic field affects its motion. So this is a defect of Bohr model, and this effect, the splitting of the line in the presence of magnetic field, is known as Zeeman effect. Also, if the hydrogen gas was submitted to an electrical field, we have a splitting of the line to several lines, and Bohr could not explain why. And the same observation in the presence of electrical field, this is the Stark effect. So Stark and Zeeman proved that the motion of the electron is not protected on the orbit, and this is a defect of Bohr model. So what was the solution of Bohr? Bohr told us that the electron is found on orbit around the nucleus, but later we will prove that the motion of the electron is not in the single plane, is not on orbit, but the motion of the electron is in the three-dimensional space. I will explain this later. The main defect of Bohr model, Bohr determined the position and the speed of the electron on orbit. Suppose an electron is on orbit n, Bohr determined the radius r equal 0.53 n square angstrom. And he determined also the speed of the electron on the orbit by the relation mvr equal nh over 2 pi. So according to Bohr, when we know the orbit, we can determine the position of the electron and the speed of this electron at the same time. Later, we will prove that this is not true. So why Bohr theory could not be applied for the polyelectronic system? Suppose we have helium with Z equal 2, so we have two electrons around the nucleus. The types of interactions, we have electron repulsion, and we have electron-proton attractions. And in case of Bohr model, we have one electron. So we talk only about the attraction of electron to the nucleus. In the polyelectronic system, we have to consider in the calculation the repulsion between the electrons and the attraction between the second electron and the nucleus. For this reason, Bohr model could not be applied for polyelectronic system, because Bohr in his calculation consider only the attraction of electron to the nucleus. So Bohr formulas are only applied for hydrogen, which is a system of 1 electron and 1 proton, and hydrogen-like 1 electron and several protons. As a conclusion, Bohr formulas are only applied for systems of 1 electron, or we say for monoelectronic systems. The summary of Bohr formulas for hydrogen and hydrogen-like: Rydberg-Balmer formulas for hydrogen atom and hydrogenoid species is given by 1 over lambda equal RH Z square 1 over N square minus 1 over M square, and for hydrogen Z equal 1, so we obtain the formula we proved before, and for hydrogenoid we have to put the value of Z. Bohr model. According to Bohr model, the energy of the orbit N is given by the formula En equal minus 13.6 Z square divided by N square in electron volt, or minus 2.18 times 10 minus 18 Z square divided by N square in joule. The radius of Bohr in hydrogen atom or hydrogenoid or hydrogen-like atoms is given by R equal 53 N square Z, and R is given in this case in picometer.